All right, let's look at another application of substituting in differential equations. And that's going to be in linearizing differential equations, so we can do some more qualitative analysis. Because again, changing variables is useful for analytic methods as well as qualitative analysis. And here we're going to focus on another way of doing that qualitative analysis with changing variables. So we're going to start by considering a problem. I want you to see if you can recognize this differential equation, 0.06p times 1 minus p over 500. And hopefully you look at this and you say, oh, this is the logistic growth model. That's my growth constant, and that is my carrying capacity. Okay, and we know a lot of things about this model. We know how it behaves. We know how the graph looks like. We know how the solutions look like. But let's say that we were curious about doing some more qualitative analysis of a different sort. So specifically, if you've seen, the graph of this, right? We have those two equilibrium solutions, and we know that we kind of have this sort of thing. And then the idea being is let's kind of zoom in on very small populations, and let's zoom in on populations that are very close to the carrying capacity. Oftentimes, we might want to see very local behavior near equilibria. And the way that we're going to do that is through linearization. We're going to linearize around the equilibrium to say, okay, if we're very close to that equilibrium, how does the solution really behave? And again, we know visually, but what equation is it going to look like very close to there? And so here, again, if we're very far from the carrying capacity, we know, let's forget about math for a second, or at least a little math. If we're very close to 0, according to the logistic growth model, if we're very far from the carrying capacity, we're going to model exponential growth. Populations tend to grow exponentially unless there's other things going on. So if we look at linear behavior near this equilibrium value of 0, then we should expect something like exponential growth. How do we think populations will be here? Well, that's maybe a bit more of an interesting question, a bit harder of an answer. And again, one of the reasons in the context of the application for the growth of populations why we might be curious about that, especially the second question is, what if we have a population that really is following this model pretty well, and we have some I was going to say throw up, but that's really not the term. We have some disaster that shakes this, like breaks, it's not part of the model. Just all of a sudden something happens, maybe a meteor strikes the earth. I don't know. That's maybe humans do something to populations of animals as humans are wont to do. And, maybe this gets like bopped. It's like, oh, we used to be here and now we're here. We still expect, if everything else in the model is the same, that we're going to return to the equilibrium point. And the question is, how long do we think it'll take to get close? How do we think it's going to grow? And stuff like that. Okay, a small perturbation of the solution is going to be really what we're going to consider, and that's a very common type of analysis in higher level applied mathematics. Okay, so enough talking. Let's do it. So what we're going to do, this method of linearization, is we're going to look at this equation, and we're going to actually distribute. And we notice when we distribute, we get 0.06p minus, and I'm going to rewrite this in a very interesting way. Well, not that interesting, let's be honest. It's p squared, right? We know this is a quadratic. We know if I graph, on the p, f of p plane, right? We have, this is what f of p looks like. Reminder, this over here is time and population. Always label your axes. It really does matter for this class. Okay. F of p should probably have 2 parentheses. All right. So we know what all this stuff looks like. And we know that really locally, if we're really only looking near the equilibrium of 0, quadratic functions kind of look like a line if you zoom in. And in fact, any function, any continuous function looks like a line if you zoom in far enough. That's what linearization is all about, is saying, let's zoom in and say it looks like a line. Mathematically, what that means is if p is close to 0, what do we have? Well, if p is close to 0, squaring something makes it really small. So if p is close to 0, then this term is basically 0. So if p is close to 0, then we can approximate our differential equation with just the linear term. Oh, okay. So again, the idea being that if we're curious around here, we'll zoom in over here. Zooming around here looks like a line. What line? This line. All right. And we know how to solve this. This is exponential growth. This is literally the differential equation for exponential growth. And we know that the solution looks like P of t is just some initial population times e to the 0.06 t. All right. So that answers the less interesting question. If the population's close to 0, how does it behave? Oh, it's exponential growth. Yeah, we knew that. This is just kind of practice. Also, you might be noticing, Jason, this didn't have anything to do with substitution. Why is this in Appendix A? It's because we're going to look at this next one. Right? Again, if we zoom in around here, this is also going to look like a line. So let's do that. Right? So if P is really close to 500, what's going to happen? It's a little harder to see, but if P is really close to 500, right, this gets really close to 0. This is kind of weird. It's not as easy to see this way, but you know how it could be really easy to see? With a substitution, right? So right, if P is close to 500, it's this term that's getting close to 0. Let's let this be a new variable. Let u be 1 minus p over 500. Okay. U is going to be 1 minus p over 500. All right. So then again, if p is close to 500, what is u close to? If p is close to 500, u is close to 0. Then again, what is du dt? We're going to d dt both sides. We're going to get negative 1 over 500 dp dt. And we can rewrite our original differential equation. So it was dp dt, which is negative 500 du dt equals 0.06 times p. What is p? Oh, we never solved for it. 1 minus u times 500. Right, p over 500. Subtract it over, yep, that checks out. So this now becomes 500 times 1 minus u. And then again, 1 minus p over 500 is literally u. So you can do all this out, adjust some things. I'm a little nervous about this negative, but I'm sure it's fine. All right, these 500s cancel. And we get a new differential equation of du dt equals negative point. Oh yeah, this is fine. We get something very similar, right? This is a very similar differential equation with one very important difference, the negative. That negative is really important, right? Because there's qualitatively something very different happening at p equals 0 and p equals carrying capacity. Right? One, we're exponentially growing away from it. The other, we're exponentially approaching it. So if we linearize here, we're curious about how this behaves when p is close to 500, which is how this behaves when u is close to 0. And again, just like before, we could distribute. Negative 0.06 u plus 0.06 u squared. And just like before, if u is close to 0, this is basically 0. Right? We can basically kind of ignore it. And this is a very common thing, like not just in differential equations, but in higher level math, of just looking at quantities that are very close to zero. Then if we square them or cube them or raise them to the fourth power, they're insanely close to zero. All right. So if we're close to zero, those higher order terms basically do nothing. Don't believe me? Actually, like, check it out, right? Don't want to show it too much right now, but it's kind of similar to what we were looking for in 1.8, I believe, when we were looking at the homogeneous solution and the particular solution and those steady state solutions. And sometimes that homogeneous general solution is going to decay off to zero really quickly. It's kind of the same idea, but instead of long-term behavior, it's local behavior. So what is our conclusion? Our conclusion is near P being close to 500, and again, that's where U is close to zero. Our differential equation is basically just negative 0.06 U, which again, we know exactly what this looks like. This is exponential decay, right? This is again, just U is just some constant, e to the negative 0.06 t. So we get something very interesting, right? If the population is close to zero, we have exponential growth of this growth constant. If the hold on, we should do a substitution here. If the population is close to 500, we also get the exponential decay with a different constant, but let's compare apples to apples. What was U? U was 1 minus P over 500. So let's actually see what P is, okay? So U is 1 minus P over 500, and we know that's C e to the negative 0.06 t. So again, if we're solving for P, subtract 1, multiply by negative 500, still some constant, and we get this. So again, it's still exponential decay, just being bumped up, a vertical translation of 500. And so again, this makes sense. All right, if we zoom in over here, it's exponential decay approaching 500, the carrying capacity. If we zoom in here, what do we have? Exponential growth. And we can see that second one, especially, here's an image from the textbook of here showing you, oh yeah, here's what U behaves like when U is close to zero, right? Exponentially decaying towards zero. And again, when we translate our variables back, that's P exponentially decaying to that 500 that we just showed. All right, so again, that is a way that we can look at local behavior. And so that really answers some questions. And again, there's a lot of times with qualitative analysis, in math, we often get tricked into thinking, oh, there's a final answer. There's a number. When we have these qualitative analysis videos, right, the whole thing is the answer. It's a discovery. It's a gathering of information. So I'm like boxing this, but this is not the answer, right? This is something important. All right, so I want to be very clear. I'm not boxing an answer. I'm boxing something that's important, right? We know that as the population is close to zero, this is really how it behaves locally. As the population is close to 500, this is how it behaves locally. And of course, we know the solution to the logistic growth problem. We can actually find this, the whole thing. This is just a demonstration of the linearization method of how do we analyze close to an equilibrium point. And we can do that by essentially looking at things close to zero, and then the squared terms go away. And if something's not a zero equilibrium, we do a change of variables so that we can do the method to make it close to zero. All right. We could do this for kind of really any differential equation. All right. Really much easier with polynomial right-hand sides, but again, we can do this with anything, and that's linearization. So to kind of summarize, right, what are we doing here for linearization? Well, we're changing the variables to look at equilibria, an equilibrium point of zero. So in the last example, we only had to change the variable for one of the equilibrium points. Because one of the equilibrium points was already 0, we didn't have to do a change of variables that time. All right, and then essentially we're ignoring the nonlinear terms to get local, and then again, we can solve to get local behavior around that equilibrium. And that's what this technique of linearization is really all about. Locally, what's happening around an equilibrium point. Sometimes we can't find the full solution, but we can linearize. That makes the equation a lot simpler, and we can see how things are behaving locally. Again, another caveat, this is an autonomous differential equation. Autonomous differential equations are much simpler and honestly kind of behave very similarly to each other, right? If you think about all the slope fields and all the like solution diagrams of all the autonomous differential equations we've been solving, they all look kind of similar. But again, this technique can also be used for more complicated equations as well. Speaking of more complicated equations, we have the last video of Appendix A coming right up after this. It is going to be wild. You're going to have a good time. Anyway, bye-bye.